Welcome to the Isaac Newton Institute. My name is Christy and I'm Deputy Director here. It gives me such pleasure to welcome you all here, particularly since we didn't manage to hold the in-person event last year. We had to do it all online. And it's lovely to see so many of you actually here in person, and also there's a lot of people watching online as well. So before I introduce our wonderful speaker for today, let me just tell you a little bit about the Isaac Newton Institute. So it's a mathematics visitor research institute where we attract the best mathematicians from across the globe who come here to interact for up to 6 months at a time, and on a themed program, and they all exchange ideas together, and they really push the boundaries of mathematics, and it's always on a particular theme, the different programs. So we've got, for instance, one of our programs on at the moment here is on turbulence. We've had so the mathematics of turbulence. Then we've had programs on the mathematics of forensic science, the mathematics of melt in the mantle, and then also some very, very pure abstract mathematics as well. So it's right across the spectrum that we run these programs. And people gather together, and this sort of sums up the atmosphere. You can see how closely people are working. We've got over 130 square meters of blackboards in this building, and you see people just gathered around them the whole time, just bouncing ideas off each other. And some amazing things happen. So does anybody know who this person in the center is? That's Sir Andrew Wiles, and he proved Fermat's last theorem, which was a result which had been outstanding for over 300 years, with people trying to prove. They didn't even know whether it was true or false. And so people were trying to find counterexamples to it or prove it. And eventually Andrew Wiles proved that. And do you see where he's standing right now? Right in that? That's exactly where I'm standing right now. So he announced his proof of Fermat right where I am now. So you're in a piece of mathematical history. It was such a famous result. There were articles all about it in Le Monde, the New York Times, as well as all the British newspapers. It was huge. And that's not the only 300-year-old conjecture that's been proved in here. Just a couple of years ago, we had Kepler's conjecture, again, 350 years old, the proof of it announced here. So amazing things happen in this place. Anyone know who any of these people are? So who do we have here? Yes. Stephen Hawking, okay. And anyone know who the other person next to him is? This is more challenging, potentially. Roger Penrose. So Stephen Hawking was one of the organizers of a program here on geometry and gravity in the Institute. So he was one of the organizers. And he and Roger Penrose, as part of that program, they held a series of seminars, 6 seminars on over the course of a workshop, followed by a panel discussion on the nature of space and time, they called this series. And it was so incredible because they really disagreed about what happened in those infinitesimal moments after the Big Bang. And it was so interesting that a whole book came out of it. So this was, it was in 1995, I think, and that book is still in press. Again, it's called On the Nature of Space and Time, which you can get in all bookshops. So it was a really big publication that came out of this seminar series that was held here in the Institute. And I thought I would just introduce a quote from Stephen Hawking, who was a wonderful friend of the Institute throughout its duration until he sadly passed away. And so really what he is saying here in this quote is all about how what we do at the Institute crosses the boundaries of subject and specialism, because that's because we bring together different communities. And one of the reasons I really wanted to put up this quote is because that beautifully leads me on to our wonderful speaker today, Anotida Madzvamuse. So I first met Anotida back in 2015 because he was the lead organizer of a program that we had that brought together mathematicians, physicists, and biologists to really exchange ideas together. And it was a really cutting-edge, innovative program because Anotida realized that it was very, very difficult for the biologists to come and spend an extended period of time in the Institute because they had their wet labs, they had their experiments running, they couldn't leave them. And so he said, okay, let's bring the Institute to the wet labs. So we had 2 coachloads of mathematicians and physicists and things all going out to Aarhus and spending a 2-week period in the labs there. And it really shed light on the mathematics. It really made a big difference. And so that's what this is all about. And I really wanted Anotida to speak to you because some people sometimes ask me about what is the math that I do at school? Why is that useful in later life? And in fact, what the Anotida draws on not only mathematics and biology, but pretty much the entirety of the mathematics toolkit. So he'll be working in geometry, he'll be doing probability, statistics, analysis, discrete analysis, continuous analysis. It really, he is pulling in on all these different branches of mathematics. So if you ever hear people saying, why is mathematics useful? Just cast your mind back to Anotida's talk. So Anotida is amazing. He is chair of mathematics and computational biology at Sussex, at the University of Sussex. And he, for early career researchers that we have in this room, he's a really amazing example of how you really need to work in academia to get the success. It doesn't come, easily. So Anotida has put in so many grant things. So he's got over £300 million of funding that he has attracted from lots of different sources. And that's a really huge work. Oh, sorry, 3 million. I said 300 million is what the, forgive me, that's what the mathematical sciences has just been recently given. That's why I've got that number in my head. But so he's pulled in this huge amounts of funding. And also, what you might not know about being a mathematician is often you need to work in different places. So as well as being educated in Zimbabwe and Cuba, Anotida has had positions in the USA, Oxford, Kenya, Turkey. I mean, really, really very, very international. So he really captures so much of what it is to be an academic. You have to pull in funding for all these places, you have jobs in different places, you travel. But most importantly of all, Anotida is one of the most special people that we have in this community. He, as I say, he was an organizer of our program, and whenever I mention Anotida's name to the members of staff, the administrative staff here, there's this kind of that goes around the room. I've never heard anybody say a bad word about him, and he's won all these awards and things, but he has done it with grace and elegance, and everybody just admiring him. And so I just thought he is the perfect role model for you all to hear speak today. So Anotida, it gives me huge pleasure to have you here. Thank you.
Thanks, Christy. Thanks, Christy. Can I switch this one? No. I think. Yeah.
And we need to switch from my slide to yours.
Yes. For the Isaac Newton Institute for inviting me to give this sort of public talk. Let's see if it connects, maybe. Yeah. So she has already given you quite a lot of information about myself, so I don't need to say much more really. I'm at Sussex, and I'm an applied mathematician. So I've gone through pure maths as well as diversifying into applied mathematics. I work with data, so I like to work with data. I work with experimentalists. I've used my experience in the last 2 years. As we all know, COVID came, and I never worked on infectious diseases, and I tried to pool my resources as well and my research team to do that, to support COVID modeling in Sussex, and that has been quite useful, working with NHS, public health authorities, and it's currently it has grown as a program within the region. And there will be a workshop probably online as well in a few weeks, maybe on the 11th of May or something like that, where we tell our story, our journey on COVID modeling. But today what I want to talk to you is something different. Yes, there's mathematics underpinning it, but I want to entertain you with the idea that mathematics can emerge from biology. Yeah, you have the biological observations, and from there we derive the mathematics. I'm not going to give you the mathematics in any way, shape, or form. There will be some, but I just want, again, to give you the notion that whatever you observe can be described mathematically. And that's the beautiful thing. But do we have all the answers? No. Yeah, I'm going to, again, give you what we have and the current state of the art in terms of modeling of cells. So I want to talk about cells walking through complex environments. This is quite important. And yeah, if you, I was going to say, because some of you, I see very young people, adults here, it's good that you're doing maths, you're excited about science. If I've worked with students in Brighton College, if you know the Brighton College, if you want to do an essay on some of these things, I'm happy to help you. And so you can email me, am328@Sussex. So if you're interested, I'm very happy to do that. So I like to also contribute. So in the news yesterday, I don't know how many of you read this paper. I was amazed that I'm giving this talk and this is just being published. It's remarkable that we want yes, it's yeah, on BBC. You can watch it on you can read it on BBC. We're dealing with cells within a 53-year-old woman. Yeah, this is the biology really. You try to mutate the cells to reach, to make them younger, feel younger, and act younger. But the question is, how do you do this? What do you do? I have no idea what they did. I haven't read the paper. It's in eLife as a journal. I am going to read it probably next week to really understand what they have done, because it's quite remarkable that we want to reduce the aging, maybe wrinkles to be younger forever, but I don't think this is, for the long term, this is possible, that we can sort of mitigate death. We will die at the end of the day. This is given, yeah. But I think what we are trying to do is maybe to provide better care in older ages. So by looking at cells, cellular behavior, we might be able to maybe make that transition better. I think that's what we want to do. So I encourage you to look at this. So they said here, researchers, this is in Cambridge actually, rejuvenated a 53-year-old skin cell, so they are equivalent, the cells themselves, they behave equivalently as those of a 23-year-old. So they are 30 years younger. How do you do this? As I said, I have no idea. I am going to look at the paper. But this is fascinating. My long-term goal as an applied mathematician would be to come up with an artificial cell. Think of this, an artificial cell where you can do experiments on it, maybe trying to do therapy or drugs, cancer drugs. Can you test them on this artificial computational cell? But there's quite a lot that you need in order to build such a cell. And we could, once you have built it, it can play a lot of roles, as I will show you. Yeah, it's quite important to understand cellular cells and their role. So the first, what is a cell? Do you know what is a cell is? Anyone who knows, who is doing biology? Probably. Don't know. I don't know. So I'll take you through this gently. Let's go through what is a cell. It's a complex entity. It's a small entity. A cell is the smallest unit that can live by its own. Yeah, also bacteria. It's one of those. And we call them unicellular here. I've given them a definition. They are microscopic. You cannot see them, of course, with your naked eye. You really need a light microscope to be able to see the cells. Yeah. So biologists, that's what they do. But they are building blocks of all living organisms. So they are essential to us, as well as to plants and other organisms. It's very important. Yeah. They are primarily made out of molecules and organisms, but here is a single cell, and I will just try to go through this, but first of all, I just want to give you some definitions of what this will be. It's enclosed here by the cell membrane here, and what is inside the cell is quite complicated. Yeah, it's as I will describe again in a few minutes. But many cells, when they come together, they form tissue and organisms, so organs. In terms of the brain, the heart, the limb, and so on, they form these organs. So if we can develop these artificial cells, we might be able to maybe generate new limbs, for example. Yeah, for medical purposes. Yeah. So cells can group together to make tissue, skin, and individual organs. There are two types of cells that are eukaryotic cells, as well as these cells that are bacteria. So these they have a nucleus. Actually, the difference between these two is just one of them has a nucleus, and the other ones do not have a nucleus. And again, the nucleus is located in the center of the cell. Here is the heaviest part of the cell. That's also well known. So in terms of again, the cell, you have the membrane, as I said, the cell membrane here, and you have the nucleus. Outside of this nucleus, you have a lot of structure that is made out of, for example, microtubules, where you have proteins that work on dynein, for example, that work on microtubules. So in humans, for example, I don't know how many of you know how many cells there are in a human body. 10 to the power 13, that's almost 100,000 billions of cells in a human body. So again, we want to understand these cells. In terms of their scales, cells, if you look at the diameter of a cell, yeah, they range from 1 micrometer to about 100 micrometers. So this is the cell. So cell in terms of cells, there cells play a pivotal role in terms of you have cell. Yeah. You have a cell. Again, I've described what is a cell. In terms of mathematics, maybe I should. Sorry, I'm really sorry. I should focus here. It's my first talk, maybe at a public talk, but all I'm saying is we have a single cell, and we have a cell. And it's yeah. Really, I'm sorry again. This is not good. This has happened to me before, but I've described to you what is a cell, and in terms of mathematics, we want to understand the cell structure of okay, maybe, yeah. Yeah, I'll take 5 minutes. Sorry, I'll start again. Okay, done. Sorry. Yes. No, I'm not good, because what I want to describe to you is a single a cell, and which I haven't done very well. But all I'm saying is I'm interested in understanding the cell structure, the cell in terms of mathematics. So that maybe I should not mix with mathematics. Okay. Why am I interested in cells? I'll just go forward and describe why I'm interested in cells. They are good cells in terms of they can help with development. So in terms of wound healing, if you burn yourself, you can observe cells moving helping the wound to heal. So they're important in that case. I have talked about organ and limb development for cells, for the formation of artificial cells, also for tissue repair, as I gave you the example on the news in terms of they can help us again. I just give you some examples here. Let me talk about the bed cells. They're responsible for diseases such as cancer, for example. We are talking about brain cancer, breast cancer, for example. I have some examples here of red blood cells interacting with cancer cells, really. And this is another cancer cell, I think, for leukemia. And this is the cervical cancer cells. They are also are responsible for Alzheimer, for example, or neurodegenerative diseases. So that's the bad thing about cancer. When cancer cells mutate and during development, sometimes they become the bad guys, the bad cells. Okay. In terms of, I've said, okay, what is my talk? My talk is how cells walk through complex environments. There are two types of environments that I'm looking at. So in experiments, they do experiments on 2D substrates. Yeah. While in 3D, it's quite difficult to do experiments in 3D. Okay, I'll show you why. And the cells working on 2D, how they work on 2D is different from how they work in 3D. Again, I'll give you an example. So what in terms of just the biological observations, this is again experimentally. You have a cell here which is adhering on a 2D substrate. It's moving in this direction. The front part of the cell is called the lamellipodium, and you have a nucleus here again. You have the back end of the cell. This is just a schematic representation. I haven't described in any detail what makes this cell. I tried to do that in the previous one, but not so good. So there's quite a lot of material mechanics, biochemistry that's taking place in terms of the molecules, in terms of the structure of the cell. So how it's moving on this substrate is driven by the mechanics and the chemistry. Again, I'll talk about this in the next slides. So let's say it's attached. These are focal adhesions here that the cell, a cell doesn't have a feet, it doesn't have arms, so it cannot just hold onto environments. And so it has to find a different way of walking. And how does it do that? It protrudes the lamellipodium to the front. It stretches a little bit and forms this new adhesion. It attaches, and at the back, it tries to dislocate or detach the focal adhesion at the back end, again through a molecular species that drives this to be able to be done, and then it relocates and starts to move on this 2D substrate. Yeah, and so but this is just a schematic representation. In terms of the biology, there's quite a lot of information or processes that are responsible for cell migration. I'll just give you, maybe this might calm me down. Sorry, yes, I said. You know, some movies showing cells, how cells are moving on a complex, not on a complex environment, it's just on a 2D substrate. From a mathematical point of view, I don't know what you are thinking in terms of when you see this cell, it's moving. What mathematical quantities do you observe? You observe geometry, that the geometry is almost spherical, for example. That's one part. You also observe spirals that are forming during migration. So again, spirals, how can we model such processes? You can see the nucleus in the middle. Yeah, you have the nucleus and the back end. I don't know whether you can, do you have, or maybe I should use this. At the back end, you can see some sort of threads, very tiny threads, and these are part of the back end of the cell. Already, when the cell is migrating, it has already identified what is its front and what is its back. But I'll again give you a better movie that will demonstrate that. Okay, so this cell is very good. It's moving, but its shape is not changing substantially. It's not changing that much. Yeah. So that's one cell. In fact, the first cell is a keratocyte, and now we have a neutrophil cell. which is again moving on a 2D substrate. It's forming these what we call pseudopods. It's remarkable. Maybe when let me start again with the video. Maybe not this one. You can see the pseudopods. They are here. They form 2 of them, and immediately there's think of this as if you look at the membrane of the cell, it forms these pseudopods, and these pseudopods are bifurcating in some sense. The membrane itself is forming these. Again, the best way is just pseudopods, really, and it's retracting them if it chooses to go in the other direction. Yeah, so it's moving, and you see 2 pseudopods, but one of them is pulled back as the cell preferentially moves in the other direction. So there's quite a lot of dynamics in this, and from my point of view, I'm looking at again geometry, the changes in geometry, the changes in manifold. At the moment, you don't see the biochemistry. You can see maybe the mechanics of the cell as it is moving. Yeah. So let's see if I can go to the next slide. Maybe this one. This is a nice movie because it shows again these filaments at the back end, but you have the lamellipodium at the front end, and you have again filaments which sense the environment. Sensing the environments, I have shaded. Experimentalists have injected what they call green fluorescent proteins to highlight some of the molecular species that are in the cell. And this is again given here. You can see with the green, you can see some of. Let's see if it is playing. Yeah. You see, these are focal adhesions that are forming here. The focal adhesions, the cell is adhering and it's moving. At the back end, it's sort of removing these focal adhesions and moving forward. Yeah. Let's see again in order to understand the front and the back of a cell. Yeah. It's not so clear the movie, but you can see that at some point the cell becomes almost spherical. It's trying to sense the environment, and then suddenly it forms, it identifies where it's going to go, and there are green sort of proteins that you can see at the end, which are concentrated at the front end, and these are actin molecules that help the cell to identify what is its front, and where they are concentrated, it moves preferentially in that direction. At the back end, you have red proteins, which are again highlighted through the light microscopy, and so they help the cell to contract. Once it's contracted, it can move forward. Yeah. So I'm describing here the biochemistry, the molecular species that are reacting and diffusing within these environments, and they break symmetry to be concentrated either at the front end or at the back end, and they help the cell to sense, to sort of say, okay, in this direction, that's where my front should be, and at the back are the myosin. The red ones are actually myosin, and at the front they are actin species. I'll give you this movie again to demonstrate to some extent the formation of this front end of a cell. This is a computational cell that I'm illustrating here. Yeah. So again, we are solving complex models here to be able to generate the front of this cell. It's not moving at the moment, it's just a stationary cell, but I'm looking at what we call polarization of molecular species. Yeah? When the cell, before it moves, it has to identify what's its front and its back. Yeah. Let's go to 3D. Yeah. This was in 2D. Let's look at 3D in terms of our cells again. So this movie has 3 channels. You have just to see the cell on a complex in 3D complex environment, and you can now see through another channel how the cell is moving. It's better on my computer because I guess it's much clearer. But you can see the front end. It's really trying to move through this. It's not clear here at all. These fibers. The 3D environment normally it's formed experimentally. This is in experiments. It's formed of collagen, and collagen is representative of maybe tissue, for example. Yeah, and they can observe how these cells are moving through these complex environments. So again, I'm looking at cells that are moving either on 2D substrates or in 3D. Yeah, and we want to be able to model these. Let's see if I can go to the next movie. Yeah, hopefully this is better. Can you see by any chance? This is the lamellar podium. It's quite lengthy. Yeah, maybe I should freeze it at the very beginning. Then you can. Yeah. If you can see here, look at the lamella. It's really it's well stretched, very far away from the nucleus. As I said, the nucleus is the heaviest part of the cell, and it really can hinder or promote cell migration depending on the environment. If the environment is too dense, the cell will struggle to move through this dense environment. And the front end is sensing the pores, which pores are better for the cell to be able to migrate through. Another thing that you can observe is at the back end there is another cell that's following almost. Maybe it's not coming up on this movie, maybe. Yeah. All I'm saying is the leading cell can lead other cells at the back also to migrate through the same pathways. How do they see this? They are sensing also the cell that is in front of it. Not only the environment, but they can also sense. So there is cell-to-cell interaction, which also we need to be able to account for. Let's see if I can move to the next one, which is this. This is a mathematical sort of representation. Let's see. Yeah, a mathematical representation of this movie in. Yeah, I have the same movie here, and I have a representation of a segmentation, you can think of it, or cell tracking of this cell when it's moving. This is a computational representation of this, and currently in many works they are just, as an example for this one, you can just follow the centroid of this cell. The central position, you can compute it geometrically, and you can tell the pathway, the locus followed by the cell. But more importantly, I'm interested in the shape of the cell and how it's deforming. This is just the nucleus that's following the nucleus, for example, pathways for the nucleus, and you can have an outline of the general sort of direction of the movement. In terms of the mathematics, I'll just describe one. The model that I'm going to describe follows very much Newton's second law of motion, which I put at on the very first slide, which is force is equal to mass times acceleration. You have a force balance. You have force, you have mass times acceleration as a force balance. I'm going to assume a force balance of only forces that are acting only on the cell membrane. So if I can have a chalk somewhere, as a mathematician, I should be able to do this. So this is my cell, and I just have the membrane. I ignore everything that's inside. I just want to follow the cell, the cell membrane, and I'm just going to assume that there are forces here that act on every point on this membrane in the normal direction. And that's my normal direction is mu. In fact, it's mu according to that. And this force is given by a summation of all these forces. I balance them on this membrane, and I try to follow the dynamics of this membrane. This is a very simplified model where I'm ignoring exactly everything that's inside, and I take into account the environment through the F external. So the forces, external forces are coming through that. The other forces that I have here, are driven by the molecular species that are residing on this membrane. So I call them protrusive forces, and these are driven by the molecular species in the vicinity of the cell membrane. They also react and diffuse, so it leads naturally to what we call reaction diffusion systems. I also need to allow volume constraints. As you can see from the movies, the volume is not always constant, it's changing Also due to osmosis, sometimes it changes. It's never constant, the volume of the cell. You can compute it. I'm going to assume also this FV to be a viscous force. Again, that's proportional to the material velocity, just the rate of change of these points that are here, and that's this term here. This term, sorry, the viscous. This is the volume constraint term. So what else do I have? This membrane, I'm going to assume that it has energy in it, because it's energetic, it's changing all the time, so it has some energy. And I have two types of energy here. I have the surface energy here, and I have the bending energy, which you can model. And when we do this, when you put all this together and solve it mathematically, again, I'm not going to solve the models, I'm not going to do anything, but this is a typical sort of a cell that we have in 3D, and it has two pseudopods. As I said, they are the pseudopods that are forming at the front end, yeah? And we want to follow the dynamics of such a cell, but as I said, in 3D, but if you see my cell, what makes up this cell? Can you tell me? How am I describing it? Do you see anything peculiar about this cell? It's made out of triangles. There are triangles that are joined together. Yeah, and this is the basis of what we call the finite elements, yeah, method as a numerical method for solving these complex models on surfaces, for example. So the cell is, think of a football ball that it has patches. If you look at a football ball, it has patches, but they are normally square patches or rectangular patches. Here I'm assuming that my patches on the ball, if you start with a cell that is a ball, are just simply triangles. Yeah, and then they deform during migration. So can we capture some of the dynamics? In particular, we are inspired to do this by this very nice movie. Let's see if I can show it. Again, let's see if it, the resolution is not very good, but let's see. Do you see the movie? Yeah, it's a neutrophil cell again. It's chasing bacteria. At the front end, there's bacteria here. It wants to eat. We all feel hungry. When we are hungry, we go to the restaurant or to a dining hall and we eat. But for the cell, it has to catch its food. So it's moving around these obstacles, very complex obstacles, and it's moving them. It's moving them around, and in doing so, it finally captures the bacteria and eats. So again, I'll play the movie. It's very important. There are lots of things here that are happening. I could spend a considerable amount of time describing this. It's a cell that's in a complex environment. The environment is made out of deformable objects, which it can move. And that's important as well, to replicate in the mathematics. Yeah, its geometry is changing as well. It's forming these pseudopods as well. So can we capture this as a toy, as a mathematical toy for, here we are. This is now a computational cell, which captures, the idea is to capture the dynamics that you observe experimentally. Yes, there are other things that we need to do much more to fit this to experiments and so on and other things, but from a conceptual point of view, we are able to replicate the dynamics that you see experimentally. And using that model that I just showed you. The other thing is we want to be able to form tissue, but tissues are formed, as I said, with multicellular cells. When cells come together, they form an organ. Can we model these cells from single cells to a clustering of cells? Remember, I am solving, and this is important, on each cell, I have a system, a very complicated system of mathematics on it that I'm solving. And if I have, let's say, 10 cells, 20 cells, I need to solve these systems of models on each one of them, and then bring all that models together in an integrated framework. Yeah. So let's see again how this pans out. Again, what did I put in them? I just put a source in the middle so that they can be attracted to that source, and the cells are moving and forming a cluster around that source. Yeah. So again, it's a conceptual framework where we can now study how cells come together to interact together, and probably we can start to address the formation of small organs or something like that. Yeah. So one of them, and the last one that I want to show in this sort of models that are only posed on the surface is how the cell is binding to a 2D substrate within a 3D environment. It's a uniform environment. Again, this is again a caricature. It's nowhere near the full reality. But again, it's a cell that's going to adhere on a substrate, and it's supposed to pull out at the back end and be able to. But this is a computational, it's a mathematical model that's giving rise to this. What you should observe is at the very beginning, the cell is spherical. And as I said, I have molecular species that can break symmetry depending on their dynamics, and they can sort of give rise to the cell, indicate to the cell what is its front and its back. You see that the red concentration, these are maybe acting, for example, which are at the front end. It helps the cell to move preferentially in that direction. While at the back end, the blue ones, you can consider that as myosin. And so you can see the cell is moving preferentially where the higher acting concentrations are, and it's attaching again. So this is, again, you can think of this as the formation of focal adhesions as observed in experiments. Then the next example I want to demonstrate to you, I have spoken about wound healing, yeah? That if you cut your wound, then cells will help the wound to heal. How do we know about this? This is the question. How do we know that cells help with this, with wound healing? This is an example of a zebrafish cell. It's a juvenile. It's small, maybe less than 3 centimeters, very tiny. You put it under a microscope. This is in vivo, in real life. Yeah. You can see everything. With the zebrafish, it's very transparent under microscopy. You can see the bone structure. You can see everything in the zebrafish. In particular, if we pass through these green fluorescent proteins, we can see the molecular species inside the cell during real time. Yeah. So what biologists have done is, okay, they put the zebrafish onto their experiment, and they make a cut at the back end or the tail end. And this is what they observe. Again, this is in real time. This is a physical organism. So they observe here neutrophil cells migrating towards the wound. The wound is up here. Yeah, they are migrating all the way, trying to help the wound to heal. And they stimulate the tissue and everything else in order for it to heal better. You can also observe, I don't know if you can see, but they are quite difficult to see. There are some movement at the back end. There are also, you can see some cells that are moving at the back end. They are quite difficult. They haven't been highlighted itself, but they are also helping the wound to heal as well. Yeah, neutrophil cells are very good. So when we got these experiments, we asked, okay, what have you done? All they did was to track the centroid positions again, to be able to quantify the direction in which the cells are moving. But by doing this, they ignored the morphology of the cell. Yeah? And they wanted to understand how the cell is migrating, but through the morphological changes. And they could also, and this was also important, they could reconstruct 3D images, but only with very few cross sections. And so the data is not very rich, but at least it gives them the notion that they can follow these cells in 3D. Yeah. What else? This project came from a biomedical engineer, and he gave us again these sort of Z cross sections of a single cell. Think of a one cell starting from the blue one. It migrates in the next time to the green one, and over a certain time period, you can follow the pathways of the cell as it moves across the substrate. Yeah, but the shape is changing, shape morphology is changing. Also, the direction is also changing. The question he asked us, can you come up with a mathematical model that can describe the dynamics, the full dynamics of this cell given only images? There is no biochemistry, there is no mechanics. They give us only the images. Can you construct a mathematical model? This was very difficult, and it took us quite a while to figure out that the only way to do this was to come up with an optimal control, think about optimal control models in transport and so on, but for this particular problem. So the model is here. I'm just going to describe it again in very simple terms. We are just going to solve the model only on the, all we are given are, all we are given are just these manifolds here, which are changing. So these are the surfaces, the membranes of the cells. That's all we are given, nothing else. So we are going to try to pose a model only on these time-dependent manifolds gamma of t, which are in the normal direction. Again, this is the velocity of each material point. Now we have a function. I'm going to describe this because it's a very important function. It's an eta function that allows this model, if we can solve it efficiently, to fit to data. We don't know this function at all. We have to find it. And it's not easy to find it. The rest is given. This is volume constraint. We can, even given a cell, we can compute its volume, so it's very good. This is a regularization term in order for this model to be well posed, but it has mean curvature. I don't know how many of you know, probably you know about mean curvature to some extent. If you compute the curvature in this will be a negative one, this will be a positive. It gives you how the membrane is protruding outside or inside. That's what mean curvature will describe you for. So again, we can compute this given the manifold. So everything else is these two are well known, but it's the eta function. The eta function helps us to the model to fit to data in as close as possible. Mathematically, the closeness is not well defined for these kind of problems. It's quite difficult to define the notion of closeness. We can, but then it turns out it's not differentiable. That's another mathematical problem altogether. So that's one problem. The other problem is we don't really know the regularity of this eta, how it behaves as a function. We don't know. We know very little of it. So I give you this model, but I'm going to throw it through the window because it's useless, completely useless. It's a good model, but it doesn't do the job. So what we do in the next slide is to think of this rather than solving on this manifold. I'm just going to embed, I lost my chalk probably somewhere.
It's not from the board.
Yeah, that's enough. Yeah, I'm just going to embed this cell in a much bigger domain such that I can find a function. I'll call it phi function. It has value 1 here. It has value -1 here. And it will have value 0 over here. I make it smooth because otherwise it will be a discontinuous function. I make it smooth so that it can help me to identify what is the inside of the cell, yeah, and what is the outside of the cell. And by doing this, I can not only solve my model on the sharp interface, I call it, on the boundary, I now solve my model everywhere else where the two problems that I have, the definition of closeness mathematically, I can define it it's well known, I can define it very well. The regularity of this function phi, I can also establish it very well. So everything else holds. I don't care about eta. So I move my problem from eta to phi. And that's what I'm going to define. And phi is given by this. Don't worry about the equation. If phi satisfies some equation. The only thing I have to do for phi is to encode the two critical parameters that I need, the eta function and the volume constraint. That's all I care. Eta function satisfies what we call an Alan-Kahn model for phase fields. I can now define, again, the measures between data and the model. And I can define this rigorously, and I can prove everything else, existence and uniqueness of my models, and so on. So I have to solve this now to be able to fit to data, and it works very well. Otherwise, I wouldn't be giving this talk at all in this. So in terms of images, yes, you can extrapolate actually the phi function directly from the images. It's also quite, we can do this. So it's very nice. And what does it help me to do? This is a movie showing both the keratocyte cell that I showed you and the mathematics. Yeah, how these two are linked together. So I have a keratocyte cell here that's migrating, and we are capturing its evolution down here. The shape changes are not really dramatic. There are no dramatic changes in shape morphology, so it's okay. We can also quantify the physics in terms of the forces. Yeah, we can do that. So it looks like it's working, but this is on isotropic environments as well. Everything's on isotropic. I haven't spoken about complex environments at all because it's much more complicated, the problem. Yeah. And also that the experiments don't have such problems. So what about cells that exhibit complex morphological changes? And this is one of them. Can the model capture? This is a cancer cell. I got this cancer cell video from Grenoble when I gave the talk there, and you can see that the cell is migrating on this substrate, but its shape is changing substantially. And also it can break. You can see it observed experimentally that the tail end can also be separated from the front end and experimental. And the model captures this as well. Yeah. What's more important, I think, is what can we say about the biology really to biological colleagues, is that we can follow multiple cells, many cells, not only one cell. With a single model, we can follow multiple cells. In particular, and this is very important, experimentalists spend hours and hours counting how many cells are dividing. I spoke about cells being 10 to the power 13. Well, the number, this is the number. It's approximately 10 to the power 13, 10 to the power 14. Why are we not, this is number of cells. Why are we not precise? Why can we not be precise to say there are 5? Do we know? Huh? Exactly. They are constantly dividing. That's one thing. What else? They are dying. So cells are dying. They are constantly dividing. This model that I've given you can capture both of these when cells divide as well as cells are dying. So it's really a very nice model in that sense. I'm giving you here on one end. Let me see if I can play it again. On one end, I just focus on in this corner here to look at. I think I start with 3 cells, and they divide. Yeah, and you can see I'm counting. This is called Euler's number. Yeah, in terms of phase fields, I can compute what is Euler's number. Euler was very good. He did many things, and one of them was just to, from a manifold, given a well-connected manifold, can you compute how many manifolds are emerging when the cell is dividing? And this is the number that we can compute. So cell division. 5 minutes? Yes. 5. Okay. Yeah. So that's. I think it's important that we can help biologists with a ready-made tool that they can use to count the number of cells. Yeah. I shouldn't. No. Yeah. This is the slide that I want to go to. Maybe here. Okay. I should not be kidding myself. I have a very difficult problem. Yeah. The cell itself, I haven't described it in this first slide. As I said, it's my first talk in the public, and it's not very good. I apologize for that. It was difficult to know what to say, how to say it. But anyway, the cell, you have a nucleus here. Yeah, you have the nuclear envelope. You have the cytoskeleton or the cytoplasm, you can say, and the plasma membrane and the environment. What I'm proposing is a model that can integrate all these together. But as you can see, it's a mess. It's a complete mess. And in particular, when you look at the dynamics of the cell, how they migrate through these complex environments, we need to be able to capture these. Now, you have played this game, you want to be a millionaire or something like that, or you have watched football at the end of the news, BBC News on Saturday, they say if you don't want to know the score, just go and make a cup of tea. This is the time, if you don't want to see the next slide, you can go out, because the mathematics is embedded there. This is, I apologize, because this is what I'm really looking at. Yeah. I've been quite explicit in terms of what is the model for the nucleus, what is the model for the cytoplasm, and what is the model for the extracellular matrix, the complex environment. The models I have given you today, all these models, are embedded in the red ones. This is all I've done today in terms of what I've given you. I have ignored the other, so these are biochemistry. These are all the biochemistry, including the blue as well, but also they have the mechanics, I should also say, for the red ones. But the black ones that I have ignored completely, I haven't spoken about this, these are the mechanics. I want to really, a cell is mechanical properties, lots of them. It's like a viscoelastic gel, for example, and therefore, how can we represent this? And this is my model. This is the model that I'm proposing to look at how cells are migrating through complex environments. We have done some of these models where we couple mechanics with biochemistry, and we can observe cells from a very uniform, spherical shape. They form these very complicated shapes, formation of pseudopods already in 3D. But there is no, the environment is uniform. I will leave you with this movie. The challenge really is to be able, in 3D, that model, if we can solve it efficiently, everything else, we should be able to capture cells that are in such complex environments made out of fibers and so on. Yeah, and this is my goal, really. Yeah, so I will stop here and yeah, take questions.
Anotida, that was for me amazing. Now, Anotida says that he apologizes because he got tied up in his news. It doesn't do this to a public audience the whole time, but actually for me it's the opposite. We are so privileged to have absolutely cutting edge research being presented to us. It's absolutely amazing, Anotida. And I love that you moved between the mathematical modeling and the reality and really showed people how these work. And there is a lovely George Box quote that I think you should share with the audience. It's a favorite quote of yours and mine, I think.
Well, yeah, models, all models are wrong. But some of them are useful. So, yeah, again, I apologize, as I said, yeah.
Don't apologize for one moment, Anotida. That's what was perfect. Now, it might be the case that some people need to run out the door right this second. You can do that. But if anybody wants to ask questions, so if anybody wants to sneak out quickly and quietly, we won't be offended. But I'm sure there will be some questions from the audience. So yes, please.
Thank you very much. If this really was a first talk at a public audience about this topic, I'm honestly amazed. So, yeah, thanks very much for this. I have no background in biology. I have a background in software engineering, somewhat mathematics. And for me, you managed to combine both worlds in a way that I never imagined ever in my life, to be honest. So my question there is, again, from my software engineering background, how computationally demanding all these models are, and when were you dependent a lot on technological advancements on computation? Was there some time where there was computational war, basically, where you couldn't really find the resources to model all these?
Yeah, very good question. It's a difficult question to answer because most of these models you cannot just solve them on your laptop. So it's not possible. And we solve more, in particular for 3D cell migration, we solve them using clusters, HPC clusters. So yeah, we need that knowledge. But Yeah, it depends on the numerical methods, whether you can parallelize the algorithms efficiently. That will enhance. But for finite elements, which is my area that I'm using, finite elements, it's quite challenging. And therefore, we are solving, for 10 cells, 20 cells, you hope that each cell you can send it to a node and it can be solved and you can collect the data all together. But yeah, you need the computational infrastructure to be able to do this. Yes. Yeah.
Lovely question. Thank you. Do you have any more questions?
There was one here.
Yes, I mean, it was essentially the same question. I was just interested in the size of the networks that they can simulate at the same time. How many cells?
A very good point. This is, I think, since we are posing models on a single cell, and the models themselves, I could give you one, in particular, the one that I described using phase fields. If you were just to think of solving the model in 3D, yeah, this is in 3D, yeah, you have your X, you have your Y, you have your Z, and you divide your domain, whatever domain you have, into 1,000 points in this case, 1,000 points here, 1,000, or maybe 1,000 will be true. If I do 1,000, I'm already, you can compute how many there are. It's 1,000 million, it's a billion points. I have already a billion that I need. I cannot, there is no way I can solve this. But we have money to do this for 3D just using, you have really to be creative. Adaptivity mesh, adaptive algorithms, adaptive time steps for the numerical method, as well as parallelizing it, really. Yeah, I should, if I had known, I could have shown you a movie with the mesh in 3D. The mesh is only concentrated where the manifold is, and everywhere else the mesh is very coarse, because I really don't care. I care about the manifold that I'm following, and therefore one has to be innovative in terms of the technology. Yeah, absolutely. It's challenging, yes. Yeah. But my focus really is to be able to make these models fit to data, be used by experimentalists. They must be informed by experimentalists, but they must also try to inform the experiments as well as to guiding them. But if you need to do this, then you have to solve these models almost in real time. And the computations take about 2 to 3 days, some of them. If you don't do the things that I'm talking about, it could take a month to solve them. So we want to be doing this in a few hours and so on. But it's a challenge, absolutely. Yes.
Hi, thank you very much for an interesting talk. Coming from a mathematical and computational background, I have actually 2 questions for you. So nowadays we often hear about machine learning and deep learning, and I was wondering, is anyone, for example, taking videos or images from experimentalists and trying to do some sort of modeling using deep learning, like neural networks? So that would be one question. Sorry.
I follow you. Yes.
And then the second question would be, when you were drawing that on the blackboard, I was wondering, are there maybe some Monte Carlo sampling methods trying to, at least, I don't know, do some 2D modeling, if not 3D? So in short, why do you go for differential equations and partial differential equations? And why is that the route to follow for one of these processes?
Yeah, it's very difficult question. Very.
Sorry about that.
I will start with the machine learning. I think it's yes. If you want to understand the data in terms of characterizing it, in terms of classifying it, in terms of clustering, whatever you want to do, you can use those very well. The only thing that you fail to do is to be able to do the dynamics, which are really geometrical, dynamics that you care about. The shape, for example, the morphology of the cell, the mechanics of the cell. These are dynamical properties that you care about. You cannot capture. I don't know. Maybe I'm not an expert on machine learning. I'm sure someone will correct me tomorrow. I would love to see that, but I haven't seen it, and I don't think it's the appropriate approach for modeling these things. Given that, yes, I mean, if you look at images, yes, that's what we have done with with one of this model that I gave at the end for cell division. So you just read in 200 images, and it follows them. It gives you all the properties, the shell shape, curvature. You can compute everything you need with this as well, given the images. So it works very well. But if you want a dynamic model, then you have to do, and this is what they care about. They care about the dynamics, to be able to follow them, and also to make predictions in the future. It's not only that you can quantify what you see, you want to quantify what you don't see, and to be able to tell the biologists that, oh, maybe you should look in this direction, and this has happened, and they discovered new properties and so on. So that's the first thing. In terms of Monte Carlo, we use them a lot in order to fit the data. Sorry, to feed the model to data, we need some statistical method approaches, and we use Bayesian methods or optimal control, and therefore they render naturally to Monte Carlo. So we do this already. Yeah.
Thank you.
Again, very good and interesting question. One final question, yes.
Yes.
I've got one more from a sort of biology perspective. And thank you for a really interesting talk. So I'm kind of interested in how this information and these models are going to perhaps feed back into the biology research, and an idea of what medical advancements it might help with.
Yeah, I think it's very good question. Very.
Do you want to repeat the question back, Anotida?
Yeah. So the question is, how do we feed all this back to the biologists, I guess, as outcomes? So I work with experimentalists in the labs. As you said, I visit labs. So I am in the labs and I understand what are the experiments. This is important. So they drive the questions, but because we have the models, we can make predictions that they cannot do. They're not doing experiments. So we suggest to them what other avenues they could look into, and so on. So it's an iterative process really between us and them, and feeding each other, and that's it's fundamental research, but it's driven by experiments in my area, in my research group. Yeah, I'm not only looking at the theoretical models, which are fascinating. I think it's for other people to look at the analysis of these models, the existence of uniqueness and so on. Pure mathematicians they will gladly look at those, and my drive is to provide predictive models to experimentalists. Yeah.
Again, a very, very lovely question, and I will tell you a bit more about other programs we've done offline. But I'm aware of time now, so can we all just say a huge thank you to Anotida? It was amazing insight into what happens in